have actually contributed a lot towards that summability method, and many of their papers have appeared in very highly reputable journals like Proceeding Learning and Society, and it was quite frequently they were publishing. And then later part, when the subject took a different turn, then I think our contribution was not that high for a long period of time. So there was a big history. So I never worked on this as that aspect, and which led to, I'm pretty sure a lot of approximation people must be using those kind of result, which gives a faster convergence and so on and so forth. But there is a tremendous amount of contribution from the Indian school in the 50s and 60s. Okay, so today's talk would be locally compact abelian groups, some particular cases we have seen in the first lecture. And there, with the Euclidean structure, we used to get the main results about the convergence means inversion theorem and the Planck theorem. And the main ingredient of defining the Fourier transform was the e to the power in the case of the circle and e to the power ij in the case of the Rn. And those essentially characterizes all the continuous homomorphism from Rn to T or T to T. And we build up that, and then the convolution. So now when we are talking about any abstract group, then obviously, I need to click it here. Yeah. So, but before that, one need to do this one. Okay, so let's start with a locally compact abelian group or locally compact group. So group which with the topological group, and this topology locally compact. Means every neighborhood has every point has a compact neighborhood. Okay, so then Riesz representation theorem guarantees a hard measure, and through the hard measure, this is translation invariant measure. And if we can talk of the LP spaces. If we take F and G in LP, we define the convolution, which was the main ingredient when we did Fourier analysis on the Euclidean space. And is in the similar way. So one need to see in this case careful that this Y inverse and Y, this must match. It should not be. So now if I am taking F of Y, then this is G of Y inverse of X. In case of the abelian, it doesn't really matter on which side you are taking. So if you are in the non-abelian setup, you have to be extra careful about this. Okay, so now we are looking for continuous homomorphism from G to T. So for an arbitrary group, locally compact group, there is no reason to believe that such a homomorphism will exist. So that is where, as we are trying to develop from e to the power in as the avatar of the continuous homomorphism. So our first attempt would be to look for this. There will be many such groups where you may not get any non-trivial homomorphism from G to T and may not be continuous. So there probably one would like to ask that what to replace T. T is nothing but the unitary elements on C, the Hilbert space. Now one can look for the underlying Hilbert space H and the unitary operator on that underlying Hilbert space and try to look for the continuous. You may not get the continuous, but you will get something strongly continuous, so which probably will be done. Someone deals with the basic representation theory in this program. So, however, if G is locally G is abelian, then we have plenty of them. So essentially, this you can see if you have the basic representation theory notion that unitary irreducible representation separates the points. And now in Abelian Schwartz lemma tells you that it is skeletized the head in one-dimensional representation. So that is what you are doing, enough of them once you get. Okay, so that tells us to collect all those, call this as G hat. This is the dual object to the group G. And so this G hat, G is now at this stage, I am assuming that G is Abelian. So there is plenty of them. Okay, if this is very irritating. Can one take this down? Okay. Oh, that's good. Thanks. Thanks, man. So you need to take it once more. Yeah. So then G hat for Rn, as we have seen, the continuous homomorphism is going to give by Xi. So this we have seen, and if this is Tn, the torus, then we have seen it is Zn. And if it is Zn, then we get that it is Tn. Okay, so now one of the tools you know what one used to study this abstract setting was initiated by Gelfand, and he used heavily the machinery from Banach algebra. As a matter of fact, I mean, there were notion of the Banach algebra existed before Gelfand, but Gelfand is the person who really kind of systematized it and got all the required properties. So Banach algebra, quickly all of us we know that it's a Banach space, which is also an algebra, and this norm is going to kind of respect the multiplication operation, because it's an algebra, it has a ring structure. So this is xy, this product norm is dominated by the product of the norms. Okay, so then he introduced something like a spectrum of a Banach algebra B. So what is the spectrum? Spectrum is you take the elements, homomorph elements from B star, linear functional from on B, non-zero, and which is multiplicative. So essentially multiplicative homomorphism. That is the spectrum of B. Why the spectrum of a Banach space? I mean, it will be clear after a while why he called this as the spectrum. So now, if B is unital and commutative, that means if the Banach algebra having an identity and it's a commutative Banach algebra, then you look at this phi, then look at the kernel of phi. So phi is in spectrum of B, and then this kernel of phi is going to be a maximal ideal in B. That is easy to see. And then if for any maximal ideal, if you were taking M is a maximal ideal, then you consider B quotient M. That is going to be a division ring, and which obviously by the Gelfand measure would be C, and that will give you correspondence with. So now if it is unital, then this happens. There is a maximal ideal. Now also in the case of the unital commutative, then sigma B is compact Hausdorff in the Weak-Star topology. Sigma B is sitting inside B star. So in the Weak-Star topology, this is going to be compact if B is unital. And if B is not unital and commutative, you can play the same game. By every Banach algebra, you can associate a structure C, extend it to B tilde. That is going to be a unital Banach algebra. It is going to sit inside the unital Banach algebra. You play the game there, and then it is essentially the sigma B. You get now you have a unital Banach algebra commutatively. You have some sigma B tilde there. then sigma b tilde is going to be compact. And that is nothing but 1-point compactification of sigma b. So this is that sigma b is locally compact and Hausdorff space if it is non-elemental. Okay, so this is so now Gelfand had done the Gelfand theory. So for each x in B, he defined x hat on sigma B by x hat of phi. Phi is the multiplicative homomorphism, which is equal to phi of x. And this is called the Gelfand transform. X hat is called the Gelfand transform of x. Okay, so now already you have seen sigma B is locally compact, and we call this as the maximal ideal space for obvious reason that it is generating, giving each functional is giving you a maximal ideal if it is unital, so it is called the maximal ideal space. Okay. So then Gelfand showed that x hat is in C0 of sigma B. Sigma B has its own topology. Now this is going to be, in case of unital, then this is nothing but C of sigma B, because that is going to, sigma B is going to be compact. In general, this is C0 sigma B, because if sigma B is compact, then C0 sigma B is nothing but C of sigma B. Okay, and one has the control over x hat is lesser equal to norm of x. X is coming from the Banach algebra. Now, if you are doing with a unital commutative Banach algebra, then this x hat, essentially, it takes the Banach algebra sigma b to the spectrum of x. So that is why it is called the spectrum of the Banach algebra. So that is the association exact. So associate the sigma b with the spectrum of x. So that's why the nomenclature. So now come to this object, dual object G hat. So this G hat, we have already taken the continuous homomorphism to circle. And this, like, I have a gamma you can think of as a representation. So it is going to determines a non-degenerate star homomorphism of L1G on C given by, you take a f in L1, you define gamma of f is the integral over f of x gamma x dx. Now all these here are scalar valued. So I don't need to worry about the integral, and this gamma x is mod 1. So this is a nice object which exists, like become much more simpler. If it is not a scalar valued or something, then why I need to worry about the existence of the integral on L1 of G. Okay, so now G hat, we'll see that G hat can be identified with so now this is going to give a multiplicative functional, because if I take if I take f convolve with G, gamma of f convolve with G, then this is f convolve with G gamma of x dx. You write down the integral over f convolve G, then that will be integral over f of x gamma x dx into integral over gx gamma x ds, because of the translation invariance of the measure. So therefore, it's a multiplicative functional what we are defining. So it can be identified with the spectrum of the Banach algebra L1 of G. Okay, so G hat is a group. Gamma 1, gamma 2 are two characters. Then gamma 1, gamma 2 is defined to be gamma 1, gamma 2 x is equal to gamma 1 x into gamma 2 x, pointwise multiplication as before. This is going to, and obviously it is in the circle and it's a homomorphism. Therefore, gamma inverse of x is going to be gamma x bar. or gamma of X inverse, because gamma of identity is equal to 1. So now what is, so obviously when one is doing G hat, I am identifying the spectrum, then I have the topology on the spectrum what we have discussed. Now to work with the same topology, I want to find the neighborhood basis for the topology. So this is essentially would be the same as the compact open topology. So that means if I take N, I take K is a compact subset of G and R is a positive number, I find gamma is 1 minus gamma of X modulus is less than R for all X belongs to K. This compact open topology is that if X and Y are the topological space, then what you do is that you take a compact set K and you take an open set U in Y, and in CXY, the topology what you are given to the neighborhood basis at the set of all F, such that if K is contained in U. That is what is the compact open topology. So now this one can show that this is in fact the NKR is the neighborhood. There will be subbasis for the G hat, and this is the neighborhood for the identity. Then you produce the translation, you have a group structure, then you can get this subbasis for the topology of G hat. Okay. So now with this, one can show that G hat, this topology, it is easier to prove that it respects the group operation. So it's a locally compact abelian group. It's a topological group. Algebraically, we had shown that group that is easy, and then with this topology, it respects the group operation. It becomes and locally compact in that. So this agrees with the Gelfand topology, what we have discussed in the spectrum of combinant algebra. Okay, now if G is compact, then the hard measure what we are going to get, we can always normalize it. Let's call that mu G is total measure is 1. And then like you know, in the circle, what we found that e to the power in, they are orthonormal basis for L2 of T. So now one can see that the G hat is the orthonormal set in L2 of G. That is fairly trivial. So if you take two characters which are not equal, then there will be an X naught for which gamma 1, gamma 2 inverse of X naught is not equal to 1. Because gamma 1 of X naught is not equal to gamma 2 of X naught, there will be. So I just brought it to the other side. So now if I take gamma 1, gamma 2 bar of X, so I, by the translation invariance of the measure, so I have this, right? And so now I pull out this gamma 1, gamma 2 inverse of X naught. And then this is in what I have again with the translation invariant. I will get that this is gamma 1, gamma 2 inverse X dx. Now this we have assumed that it is not equal to 1. Therefore, this has to be 0. So gamma 1 and this is orthogonal, and this will be orthonormal because mod gamma is 1. Okay. So now if G is discrete, then what we see is that G hat is compact. So like Z corresponds to T. So G is discrete means L1G has a unit, namely the Dirac mass identity. So if it has a unit, the spectrum of L1G is compact. And that is identified with G hat, so G hat is compact. Now, if G is compact, then one can show that G hat is discrete. Now, from this above, I take the neighborhood of this 1 Now integral over gamma x is 0. If gamma is not is equal to 1, integral over gamma x dx is 0, right? Over the entire G. So now if I push the mod inside, then this is, now if I am taking this in the neighborhood, any neighborhood, I can now take the K, the compact set, to be the entire G. So now this is less than any half or anything what you are going to take. So then 1 is strictly less than half. So therefore, there is nothing exists in that neighborhood except for the identity. So singleton identity is an open set. So that means it is a discrete group. Okay, so now these are all the basics of the Banach algebra, what Gelfand had said and given to us. Then now one would like to define the Fourier transform exactly in an analogous fashion. So before the Fourier transform, so I have just for our convenience, I have written down the definition of the convolution. You see here, L1G is a commutative Banach algebra if G is commutative. That is, in fact, if and only if. So F convolution G, I don't care on which order. This would be equal to G convolution of F. This automatically follows. This is the definition. Here there is a typo. This would be -1. Okay. So now for F is in L1G, we define the Fourier transform as exactly in the same fashion like what we had defined for the Euclidean space. F hat of gamma is f of x gamma x inverse dx. Because we have the character, then through the character you define the Fourier transform. And then with this definition, just by the Fubini, one can get that Fg, if it is in L1 of G, then F convolution G hat is equal to F hat times G hat. Multiplication under the Fourier transform goes to the multiplication. Okay, so for each gamma in G hat, the map F going to F hat of gamma, this is a complex homomorphism from L1 of G, right? F convolution G hat equal to F hat G hat. So this is the multiplicative homomorphism. So now define gamma from L1G to C by gamma of F is equal to F hat of gamma. Then gamma of F convolution G is nothing but F hat of gamma times G hat of gamma. So that shows that this F hat is nothing but the Gelfand transform what we have seen for any Banach algebra. So then in that case, what it shows that if F is in L1, then the Gelfand transform, we had seen that it is in the C0 of the spectrum. So that is what we have identified with G hat. Now, so if F is in L1, then F hat is going to be in C0 G hat by the general Gelfand theory. Okay, so far so good. And then F hat of gamma just for the, so now this is what we have discussed, L1 to C0 G hat. Now, two important properties one would like to see it here in terms of the Fourier transform. You see, the translation is an inherent structure. These are the isometries for all LP. So now if I take the translation and take the Fourier transform, then this is going to be hit by the character. And in fact, you'll be going to hit by the character. Now, if I take the character, take a character and hit that with F, and this is certainly modulation is also part of the L1 of G. This guy becomes a function of L1 G because this is unimodular. Mod of gamma 0 is 1. So now if I take the Fourier transform, then we'll see that like in the Rn case, it will be translated on the Fourier transform side, translated by the character. So translation is going to be hit by the character in Fourier transform, and hitting a character is going to produce your translation in the Fourier transform side. Okay, so now our aim essentially is now we would like to have, once we have defined the Fourier transform, like in the other case, so what we would like to have is an inversion theorem. So now G hat is a locally compact abelian group. That's what we have seen. So it will have our measure, which is translation invariant. So now can we have the inversion? Now, if you look at the inversion in the Fourier series case, the way we have seen, if f hat is in little L1, then actually Fourier said that by the help of the Fourier's theorem, we can get that summation over f hat of n into the power I n x equal to f of x almost everywhere. Now, in the case of Rn, so we saw that if I take a nice class, Schwartz class function, then it is very nicely behaved with Fourier transform. If f is in the Schwartz space, f hat is in the Schwartz space. So therefore, we can have integral over f g hat. If both f and g are in Schwartz space, then f g hat is equal to f hat of g. With that beautiful, easy multiplication formula, we can, with the approximation with the appropriate approximate identity, we are going to get the Fourier inversion theorem. So now here one would like to have some sort of the multiplication formula where I can, because you see here there is no point like the Schwartz space. If f is in Schwartz space, f hat is in Schwartz space. Here g and g hat will be different. So I cannot take them together as an integral over f of x, g hat of x. This kind of privilege like Rn, we don't have it here. So now what kind of appropriate multiplication formula one would like to have? So there it comes that we need to consider this in terms of the measure, because every L1 is function in L1 is going to produce a regular Borel measure on the space, right? Finite regular Borel measure. Now you take Mg to be the set of all complex finite regular Borel measure on G. As a matter of fact, this is going to be a commutative Banach algebra on convolution. Fine. Okay. So then we define the Fourier-Stieltjes transform mu hat of gamma is equal to gamma x bar d mu x. So this is the Fourier-Stieltjes transform. One can show that this mu hat is continuous on G hat. It's a continuous function on G hat. Similarly, now G hat is also a locally compact abelian group. Now I take a finite measure on M of on G hat. Now I define a map from G to C as phi nu at x for each nu is nothing but integral over G hat gamma of x d nu of gamma. This integral exists because this is a bounded quantity and this is a finite measure. So this integral makes sense. So now nu going to phi nu is a non-decreasing linear injection from mg hat to set of all continuous bounded function on G. So that is fairly easy. If you take the mod of x, this is mod 1. So this is nothing but going to give you the total variation norm of nu. So this is non-decreasing linear and this injection over injection. So now if mu of nu is 0, then for every f in L1 of G, 0 is equal to f of x gamma of x d nu of gamma dx. So this is f hat of gamma. And now since f of L1 is dense in C0 G hat, this is again by the Gelfand theory. So we get that this is for all dense class function, it is scaling. So therefore, mu has to be equal to 0. Okay. So now, if you have done have gone through the this representation theorem, so it will not look very unnatural to bring out this positive definite function. So essentially, I would say that the function phi, bounded measurable function on G, is of positive type if f tilde convolve with f phi is greater or equal to 0 for all f in L1 of G. So what is f tilde? I have defined. So now f star. Can I write it here? I can go so far. So this is in fact the involution on the canonical geographic. Okay, so now I just take gamma is a bounded measurable function on G. Now I look at f star convolve with fx of gamma of x. Now this, when I do the open up the integral, this is integral over G f star of x y inverse f of y dy gamma of x dx. Now I f of y gamma of x, I can write gamma of x y inverse into gamma of y, because gamma is the homomorphism. So now fy gamma y, I will get f at. Now f of x y inverse and gamma of x y inverse, if I take the bar out, then this will be gamma of yx inverse with the change of variable. That is again f hat of gamma with a bar. So therefore, this is going to be mod of f hat of gamma bar whole square, which is a non-negative quantity. So gamma g hat is sitting inside PG, which we have a large class of examples of this. Okay. So if nu is positive, then for f is in L1 of G, f of, this is what you must be very familiar with the positive definite functions, Cj, Ck, and phi of xj, xk bar is greater or equal to 0. So this is exactly the positive definite. If I, so this is phi, phi of nu, I put it is the gamma of x d nu of x, just plugging in the definition. So what we are going to get is that this multiplied with this and this multiplied with this mod of f hat of gamma square d nu of gamma. And it's a finite measure, and this is if nu is positive measure, then this is greater or equal to 0. So therefore, phi nu belongs to PG. So if you start a new positive measure, then you get that phi nu is in PG, positive type. You have defined. So for each measure, you are defining a functions of positive type. So now is the converse true? Which means if you have functions of positive type, is it going to be phi nu for some nu, which is a finite regular Borel measure on G hat? And that is a big theorem, which is called the Buckner's theorem. In fact, that is true. Now it says that if phi is in PZ, then there exists a unique nu such that phi is equal to phi nu. Okay, so now it's a bit of a notation, just BG. I will collect all those phi mu such that mu is in MG. And BPG is BG intersection of LPG. B1G is BG intersection with L1. So this is okay. By Buckner's theorem, BG is nothing but the linear span of all those positive type. because all this phi mu and Buckner's theorem says that if you take the PG, then you are going corresponding to with the measure mu, you will get this. So now this is where we actually, with the help of the Buckner's theorem, what one can get that if I take in some function f is in g hat. Now you see the g hat, if I take a function f in L1 of g hat, then f hat is going to be on the g hat, right? So now if I am considering with in terms of the measure, I will get something like a multiplication formula over here, and in which I can prove that if Haar measure of G is fixed, then the Haar measure of G hat can be normalized so that f of x equal to f hat of gamma x d gamma for all f is in B1 of G. And then similarly, not very straightforward as usual, the Planserel theorem are difficult to prove. I mean, so but all the ingredients are now here. If you want to kind of study the Planserel proof, then after Malavika's talk, then you can also understand this Planserel theorem for this locally compact abelian. That is also true. L1 intersection L2, you define the Fourier transform, then you have the isometry, then you extend it to the entire of L2. Then also the Hausdorff-Young. So now if f is in LP, P between 1 and 2, I can break the function in L1 and L2. I can talk of the Fourier transform. So now that Fourier transform is in the LP prime. And this is the best possible index. This is in R, you can show it in terms of the dilation that the P prime is the best. Suppose if the Fourier transform of LP function takes to LQ, then Q has to be, if it is taken continuously to LQ, then Q has to be P prime, index conjugate of P. And certainly there are a lot of things about this inequality. A lot of studies has been done. For example, I mean, when does, I mean, is the, here it is the constant. So does the constant one is the best possible constant. Circle, it is best possible because you just take e to the power I, and now if you are going to any other, suppose even for R or Rn, then long back, I mean, in 70s, or 80s probably, Heat had proved that one is not the best constant for any connected abelian, locally compact abelian set. And then a Russian mathematician Bebenko proved for all those, found the best constant for Rn when P prime is an even integer. Then Beckner proved it for the entire Rn, found out the best constant, which is much less than 1. And this best constant is going to be attained by nothing else than Gaussian. So now very recently, maybe last year or a couple of years back, Michael Cowling had given this result for the Hausdorff-Young Beckner's result in much larger locally compact group. What is P prime? P prime is index conjugate to P. 1 by P plus 1 by P prime is equal to 1. So index 1. Okay, so now the question is that if I take circle, I take the dual, that is Z. Now I take the dual of Z, I'm going to get circle. If I take Rn, then the dual is Rn. Again, I take the dual, that is also Rn. So now in general, if I have a locally compact abelian group, then I know that G hat is also a locally compact abelian group. So I can define the dual object of G hat. That means G hat hat. So is this going to be the same as in the case of the Euclidean case? That's a pretty natural question to ask. And so now, this is what we are going to see in the much celebrated result. It's the Pontryagin Duality theorem. Okay, so now let me take X is in G. I define capital phi. Px is a map from G hat to C. So which means it is evaluated at gamma. This is nothing but the evaluation function gamma of X. Right. And suppose if you have a finite abelian group, let's see that what we are asking. So this is not only the Rn and Zn. If you look at the finite abelian group, then the structure theorem is going to tell you that this can be written in terms of the cyclic group. And then this is nothing but each of them are Zn. And then this Zn's dual are nothing but the Zn themselves, right? I mean, so dual you are going to get in the finite abelian group, G hat hat is also equal to G. I mean, so now for arbitrary locally compact group, we need to kind of do some work. Okay, so now this is what is, I take the evaluation map. Phi x at gamma is gamma of x. So x going to phi x is a group homomorphism from G to G hat hat. Now, so this phi x of gamma 1, gamma 2 is gamma 1x, gamma 2x. So this is phi x of gamma 1, phi x of gamma 2. So now this is modulus of this is 1. So this is going to be the character on G hat. Right. So this probably is the, so now if we can show that this is the map phi is from G to G double hat, this is an isomorphism of topological group, then we can say that G and G hat hat, they are same. And that is what is the Pontryagin duality theorem says. Okay, so little idea about what the proof is. So for each x in G, define phi x from G hat to C. That is defined. I don't know why it is repeated. So the content is maybe I have just repeated this line. So phi of x1, x2 is phi x1, phi x2. That's what we have discussed. If phi x1 is equal to phi x2, then the x1 is equal to x2 injection. I need to solve. It's an injective map. If x1 is not equal to x2, then the Gelfand theorem says that there exists a gamma with separate points. So therefore, you will get gamma x1 is not equal to gamma x2. So now phi is a group homomorphism, isomorphism. So what we want to show is mainly the topological part. Okay, suppose so which means we take a net x alpha, convert this to x in G. So now gamma of x alpha converges to gamma of x. It's a continuous map. So therefore, if I take a f is in L1 of G hat, this f hat is in L1 of G hat, then this gamma of x alpha, f hat of gamma, this will converge to gamma of x, f hat of gamma. But what we actually want it for all f in L1 of G hat. So that comes because f of B1G is the set of positive functions intersection with the L1. So they are dense in L1 of G hat. And from there, the result will follow that this is a topologically, this is continuous. Now, it remains to show that it is onto. If we can show that it is onto, then we are done. So since phi g is a subgroup and locally compact, then phi g is closed. And now you take X. Let's assume that there is a X which is not in phi g, but in G double I. So there will exist a symmetric neighborhood of identity such that X V intersection with phi g is empty, right? Phi g is closed. Therefore, I can always separate a neighborhood, small neighborhood of identity such that XVV intersection of phi g is empty. Now I take two functions, continuous function with compact support, such that support of phi is contained in XV and support of psi is contained in V. Then phi convolution of psi is not equal to 0. And support of phi or the psi intersection of phi g, because this support is going to be contained in XVV. Support of phi is in XV and support of psi is in V. Support of phi convolution psi would be in this thing XVV, and then the intersection of phi g is empty set. So phi convolution, both of them are in CCG double hat, therefore it is in B positive type on G hat hat. So therefore phi convolution of psi is equal to H hat for some H coming in BG hat. So 0 is equal to H hat of phi X inverse because of this. So which is equal to phi X of gamma, H gamma by the definition. This is equal to 0. So which means H gamma of gamma X d gamma, this is equal to 0. And that is nothing but H hat is essentially 0. H hat of everything is 0 and H is in BG hat. We have the inversion formula, therefore H is equal to 0. So therefore phi convolution of psi is equal to 0, so which is a contradiction. So it has to be onto. So now finally we can write down, because of all this Pontryagin duality, now I can say that because G hat is equal to G, therefore whatever the inversion formula we have proved through the measure on BG hat, now we can write down straight away that if F is in L1 of G and F hat of G hat, F hat is in L1 of G hat, then we can talk of the integral. Then F of X equal to F hat of gamma, gamma X d gamma, almost everywhere. Exactly, we could recover the same statement of the Fourier inversion, what we had proved for the Euclidean case. In this case, with the help of Poisson duality and Buckner's theorem. Okay, the uniqueness is that if mu and nu, this is mg, m is missing here, and mu hat is equal to nu hat, then again mu is equal to nu, the uniqueness. And this is now some more application of that, still in 2 minutes. Yeah, I won't take that. So if H is a closed subgroup of G, take the picture of R and Z in your mind. So then I define H per, which is the annihilator of H. That means all such character which annihilates every element of H. Gamma of X is equal to 1 for all X is in H. So now the theorem is that if H is a closed subgroup of G, remember that we are in a locally compact abelian group setting, commutative group, then G by H is a closed subgroup. Now this I can talk of the Fourier. What will be the Fourier transform dual object of this? Suppose R quotient of Z, the dual object if I am going to take. Suppose if I take H to be Z, then what will be H per? H per is equal to all those gamma in G hat. That means all those gamma in Z. G hat is R. All those xi in R such that e to the power 2 pi I xi dot n is equal to 1 for all n belongs to Z. So now what is the xi? It has to be integer, right? H part is nothing but the integer. So now G quotient H hat, this it can be identified with H part. And G hat is a group quotient with the H part, then this is going to be identified with H hat. Now this identification is essentially saying one important thing is that, you see, if you take H to be your Z, then H hat is nothing but T. Then this is G hat is R and H part is Z. This is our quotient Z. And now it says that if I have a character, right, this is onto, I mean, continuous and onto, I have some sort of a Hanbanach theorem going from H hat to G hat. So which means if H is a closed subgroup of H, every character on H extends to a character of G. This you will see in much glory when you do the Harishchandra's representation, when you will try to see this. This is just a baby version of the Abelian. Okay. So then very useful formula is a useful thing where the Fourier transform of R and the function and circle, it is going how they are going to be related. Can you please oh, it's not there. Okay, so now I take a F in L1 of R. Okay, so now I define F tilde of X in 0, 1. Which means I periodized it. This has become a one periodic function. Now I can talk of the Fourier coefficient of this F tilde, rather it's F sharp. The Fourier coefficient of F sharp. Now if I take the F sharp hat at M, then this is integral 0 to 1, then the sum, if you plug in the sum, make it now the sum will go from n to n plus 1 over the sum n, which will give you the integral over R. So this is going to be F hat at M. That means if you are started with R, you are getting F hat, you are restricting it to Z, and so you are getting the Fourier coefficient. Now, what does this say? Now, suppose if I have a nice class of function, the Fourier series is converging to this. So this is going to be F sharp hat at n e to the power I n x. This is equal to F sharp of n. So now this is nothing but F hat of n, and this is nothing but summation over n F of x plus. Right? This is the Poisson summation formula. So now we change the role over here. H is a closed subgroup of G. For F is in CCG, define F of x plus H is equal to integral over H F of xy dy. This is the object, where H is now the discrete measure in this case. If H is Z, now the integral is nothing but the sum. And this is precisely the capital F xh, what we are denoting there as the F sharp. Then F is in CCG by H. And F hat is the original function restricted to H perp. And F hat restricted to H perp, if F hat restricted to H perp in L1 of H perp, that's what the condition what we are imposing so that the Fourier series converges to get this line, then integral over h f of x y dy and summation over f of x plus n is equal to integral over h per f hat of gamma x dx. This is the Poisson summation formula for locally compact abelian group. As you can see that if you go beyond the abelian group, then there will be, you need to consider d by h and other thing, that will more complication. But this is a very neat and useful formula for locally compact abelian group. We capture exactly this, what is the Poisson summation formula for the Euclidean space. So I think I'll stop here. My time is over.
Any questions or comments?
So I have a tiny question. So we had Fourier transform for any general locally compact 1 and 2, thanks to Hostop.
Yeah.
And what about p greater than?
Yeah, so there we have tempered distribution, right?
General group?
No, in Rn. In Rn we have tempered distribution. So here, so now we don't have a Schwartz space, right? In this case, there is no differentiability structure. So it's a very good question. So now here, what I need to look at, something like which is giving a kind of the bounded linear function around CC of G. That is the at most the best kind of thing I can expect for. So they are called pseudo measures. So now they will be in the form of the pseudo measures. They will exist. So not very useful, but yes. Yeah. So because when you try to study essentially the convolution operator on this kind of spaces, there you need to encounter with the convolution operator multipliers, for example. There. So here also the multiplier theorem, what I had shown you about the Hormander thing, here it is something like a pseudo measure, but it's
Okay.
And but obviously because here abelian, so LP multipliers are same as the LP prime multipliers, right? Then by interpolation you get it is L2. Planseral will tell you all the bounded measurable function on G hat. So that is the saving grace. I mean, you can do some more analysis. Yeah.
Any other question or comment from anybody? Are there questions from the online audience? How do I see the comments?
Yes. Yes.
More. Okay.
I have a baby question, Professor Mohanty.
Yes. What is the question?
Yeah, Sophie here.
Hello.
Are you getting me? I'm Sophie. We just want
Oh,
to.
hi, Sophie. Good to hear your voice.
Right. Thank you.
Yeah.
I mean, about the Haar measure, let's say.
Can you, there is some echo.
Yeah, but
Is it okay now?
Yeah.
So, I mean, let's suppose that we have a locally compact group and there's a compatible metric defined on it. Like in the case of the Lebesgue measure on Rn, will the Haar measure be invariant for this rotation group with respect to the metric?
Well, I don't know exactly. There it is going to be just with the unitary matrix. So that is rotational invariant because the Jacobian we can calculate with the differential calculus to be the determinant. So here I don't know.
I mean, I haven't seen such a result anywhere in the literature.
No, I haven't studied. Yeah.
Any other question from the audience or online audience? If not, then let's thank the speaker again. So who's doing basic